So thanks everyone. So I'm going to introduce Cryo-EM, sort of a general, broad introduction to Cryo-EM. Kind of go over some of the historical developments and where we are, some of the latest developments, and how that might be relevant to the type of work that we're doing in the Hive. Begin with a brief introduction to the electron microscope and how we use it for imaging macromolecular complexes. So I'll talk about cryo-EM single particle analysis. Single particle analysis is the primary way that we in HIVE Center that we image macromolecular assemblies. Briefly describe the new detectors and how those contributed to the cryo-EM resolution revolution. Some of our latest work towards atomic resolution, really truly atomic resolution, cryo-EM, and a case study with AAV. And then talk about some of the challenges, particularly with specimen preparation and the effects of anisotropy. And if we get to it, just sort of the latest with atomic modeling. All right, so I'll start with a brief intro to the electron microscope. And an electron microscope is in many ways very similar to a light microscope. So you have an illumination source, which in the case for a light microscope is light. In an electron microscope, these are high energy electrons. You have a series of lenses. So you have a condenser lens to basically focus electromagnetic radiation onto your specimen. Onto your specimen of interest. The specimen will then diffract, scatter electromagnetic radiation, and then the objective lens will then refocus the scattered light or light waves or electron waves, and then you have a series of projection lenses for the purposes of magnification. And then you can record the real space image either with an imaging medium, so either with photographic film or a digital detector or a fluorescent screen, whatnot. So this is what a modern electron microscope looks like. So you have, or a cross section of an electron microscope. So you have an electron gun. You have so one or in one, two, or actually even three condenser lenses with condenser apertures to then select out specific electrons with a specific KV. You have so then you have a specimen port where the specimen goes in, an objective lens, so the specimen diffracts, and you have an objective lens which will then refocus the electrons. You have a number of projection lenses, intermediate lenses. So in the tiny Krios, I think we have 4 or 5 projection lenses for magnification. Then you can image you can view the image either with binoculars. We have digital recording, so with binoculars from a fluorescent screen, or we have image recording systems, so digital detectors. We used to record on photographic film. But the signal to noise ratio on photographic film is not as good as on the latest digital detectors, which I'll show you in a few slides. And so this is the modern electron microscope. This is what in this is actually F30, an FEI F30 electron microscope. Actually, it's an older generation now, or it's one of the older generation, but it was state of the art a few years ago. And basically what we did is we took something like, we took that F30 and then, or FEI, they took that F30 and then basically put it in a box. So this is what these are the electron microscopes this is what it looks like now. But of course, inside it's actually the same, inside it's the same electron microscope. And so you have the same, if you open it up, it has the same optics and so forth. One of the really major advances, actually the optics have not changed very much. The electron microscope was basically an atomic resolution instrument for half a century now. So the optics have not really changed. Well, there's been a number of developments in the 90s with field emission guns. But nonetheless, since the 90s up until today, the optics for biological TEM have actually not seen dramatic improvements. Okay, but what has improved are the detectors, and then also, sort of how we use the electron microscope. One of the things that is actually one of the major improvements that has come around in the last few years is something as relatively simple as an autoloader. So it's an autoloader for imaging, for inserting specimens, robotically inserting specimens into the EM column, and moving and piezoelectric stages for moving the specimens to your region of interest. So this is $1 million addition, but it actually, which is comparatively cheap with respect to an electron microscope. If you consider that a Titan Krios is something like $5 to $6 million. But it made a huge difference because it allows you to move precisely to the area of interest and minimize the amount of drift and movement as you're imaging. And so this makes actually a huge difference in resolution. Yeah, so this is the autoloader right here. So, and the electron microscope has been around for actually almost 100 years, since the 1930s. For the design of for the development of the electron microscope, this man right here, Ernst Ruska, he was awarded the Nobel Prize in physics in 1986 for his fundamental work in electron optics for the design of the first electron microscope. So, as I said, there are a number of analogies between light and electron optics. In EM, you have light rays. In electron microscopy, you have electrons, which contribute to forming the image. Of course, with light microscopy, the wavelength of visible light and ultraviolet light is somewhere on the order of a couple hundred nanometers. The wavelength of electrons is much smaller, so it's about 0.037 angstroms, right? So about 1/20th or something like that of an angstrom. Okay, so in principle, this is of course, so the wavelength of electromagnetic radiation, of course, is what contributes to resolution. So in principle, electrons are actually capable of much higher resolution than sub angstrom resolution. But in fact, in reality, the EM is limited for reasons that I don't really have time to get into. But in reality, the EM is actually limited to approximately 1 angstrom or so resolution. And this is mostly due to, there's a number of reasons for this, but imperfections in the lens systems, the amount of noise in the digital images that we're recording, and so forth. So in a light microscope, you're typically imaging, the medium is air. In an electron microscope, it is, you have to be under vacuum, under very, very high vacuum. And this is to eliminate any potential scattering with molecules and particulates in the column. The aperture sizes in an EM are very small, and so this actually allows you to have a reasonably large depth of field. So in principle, well, in practice, the spatial resolution in an electron microscope compared to a light microscope is, so in a light microscope it's somewhere around 0.2 microns. In an electron microscope it's 1 or a couple angstroms.
And because of the small numerical aperture, we also have we can image through reasonably thick specimens in using an electron microscope. And so, just to demonstrate what exactly I mean by this, so if this is your sample, and so these are 2 points on your sample, and your sample diffracts, your sample scatters, then the objective lens will then refocus those scattered electromagnetic radiation. The objective aperture will then filter out some of the widely scattering electrons, and so these electrons will so actually, yeah. So this is for a high NA. So actually, this is for a high NA. So regardless of the light or electron microscope. So for a high numerical aperture lens, then so these will go through, and then this is now then the focus point of these electrons, and this is the focus point of these electrons. And of course, if this is your imaging plane, then this point becomes in focus, whereas this point is no longer in focus, right? And so then you have, and so this is one of the origins of blurring. Now, with a smaller numerical aperture, which is what we have in EM, what happens is that so these 2 points. These 2 points are in this imaging plane. There are, even though the actual focal points are quite far apart, but in with respect to the resolution that we're interested in, they're actually reasonably more focused on the image. And so this allows you then to image through. This allows you then to image through thick specimens. So in practice, we can see through specimens that are a couple microns thick in an electron using electrons. Now there are a number of problems with this. So in practice, you can't really. You have multiple problems imaging through thick specimens. You have multiple scattering. You have inelastic scattering. And so there's problems associated with imaging through thick specimens, but in principle you can see through them. All right. So what we're interested in is using the electron microscope for the purposes of macromolecular structural biology. And the primary technique that we use is called single particle analysis, single particle cryo-electron microscopy. So macromolecular structural biology is, of course, critically important to understanding life at the atomic level. We're all familiar with these 3 or these 4 structures. This is the structure of DNA, or the model of the original model of DNA from Watson and Crick, which of course gave birth to the rise of molecular genetics. These are the first structures of myoglobin and hemoglobin from John Canju and Max Perutz. These were solved in 1958, 1960. These were the very first proteins that were described actually using X-ray crystallography. And of course, these structures really opened up a whole world of protein structural biology and molecular biology, actually. And then sort of more recently, this is, and over the course of the last half century, more and more proteins and molecular machines have been analyzed using methods in structural biology. This is, the prokaryotic ribosome solved by Venki Ramakrishnan, and of course it's the quintessential example of a large, complicated, heterogeneous, and very dynamic macromolecular machine. So we're interested in understanding how such machines work, and the simplest way to understand how such machines work is to look at them, is to understand their underlying structure. We do this using single particle cryo-EM. So traditionally, it's been done by X-ray crystallography. We're now doing this by cryo-EM. Very briefly, the way we do this, the way cryo-EM works is you have a specimen, which you purify a specimen from cells. You put it onto an electron microscopy grid. That grid is then plunge frozen into liquid ethane. Then you transfer the frozen sample from liquid ethane. You transfer it into an electron microscope, and you start acquiring images of these frozen hydrated preparations of macromolecular assemblies. So this is an image of a frozen hydrated preparation of GRO-EL particles. Okay, GRO-EL is a bacterial chaperone, helps to fold other proteins. Each one of these particles right here, this is an individual GRO-EL protein molecule. Okay, and so what you can see is you can see a monodispersed field of GRO-EL or of particles or putative particles. Okay, and so then the job is to during data analysis is to then select out these particles, and then through a number of image processing operations, then which I'll introduce in the next slide, come out with a three-dimensional reconstruction. And in fact, this particular part of the pipeline has been very, very actively and rapidly developing over the last 2-3 decades, and still very actively continuing to develop new tools and new methods. So so here's a grid, okay, and so you apply. Okay, so the sample is applied onto the grid. Okay, this is a cross section of macromolecular particles within a layer of vitreous or frozen hydrated ice. So then we acquire images of these molecules, right? And these images are projection images. Now, if you see so projection images of these molecules. Now, if you look closely, you will see that there's some ringing around these particles, and this ringing is caused by artifacts that are inherent to electron optics. So the mechanism by which the information content is transferred onto the imaging medium is affected, is corrupted by what's known as a contrast transfer function, which I'm not going to describe here, but basically it just has to do with how contrast is transferred and how images are corrupted in in 2D projection views. We can then correct for those corruptions computationally to recover the underlying structure. The other thing to introduce is that, of course, what we're recording are projections. Okay, so these projections, so it's essentially, you're essentially summing. So these are, the intensity values of this particular object, and then the projection is just a sum of those intensities along the z direction. Okay, but the other thing to note is that because we're recording projections, so these projections do not necessarily uniquely describe the orientations. So you might be recording a projection, but actually that projection might correspond to one of multiple different orientations, and then we can computationally figure out what are the optimal orientations. Okay, so the images are also corrupted by noise, and there are multiple sources of noise in electron microscopy. And these are, and so then these are the single particles, okay, that we would obtain. So these are individual images of particles corrupted by the CTF and with additional noise. We would align them, okay, in 2 dimensions, and then we could classify them, and then through classification we can improve the signal-to-noise ratio. Okay, so these are now class averages of that small data set. And then if you, so you have these class averages, and then if you assign the orientations, the three-dimensional orientations to those class averages, then you can come up with a three-dimensional reconstruction. So this is basically the pipeline, the image processing pipeline in a nutshell. And there are numerous ways of generating the three-dimensional reconstruction. I won't describe, well, there's been a number of ways over the years that have been introduced. One of the principal ways that, especially now, we're relying on more and more is based on the principle of common lines. So this is to say that any pairs of projection images will necessarily share at least one common line between the two, in at least one common one-dimensional line between the two in a three-dimensional within a three-dimensional Fourier transform. And this principle of common lines then allows you to search for different orientations so search for different orientations in 3 dimensions, and then lock down those two-dimensional projections. So this is just a movie demonstrating exactly what I mean. So if we have two images, these are class averages of Cryo-EM. So if we have 2 images, then we can search for their relative orientations, and so of course these relative orientations can be in different areas of 3D space. This search is computationally challenging for numerous reasons, for noise and misalignment and so forth. But once we've locked down those orientations, then we can back project those images into 3D space to form a 3D reconstruction. Okay, and as we add more and more images into the data set, that 3D reconstruction becomes better and better resolved. Okay, so you're downweighting the noise, and you're increasing the amount of signal. You're downweighting the noise in the 3-dimensional reconstruction. This is an actual experimental reconstruction of Cryo-EM. It is now low resolution by today's standards. It was high resolution a number of years ago, but it's 5 angstroms. It's quite low resolution by today's standards. All right, so neither electron microscopy nor cryo-electron microscopy is a new technique. So as I mentioned, the electron microscope has been around since the 1930s. The cryogenic part of EM, so the ability to vitrify, freeze your sample prior to imaging in an EM, really was developed. The initial ideas were introduced in 1974 by Ken Taylor and Bob Glazer with 2D crystals, but then the technology was really pioneered and developed by Jacques Dubochet throughout the bulk of the 80s, where he developed the actual instruments so the plungers, the instruments that allowed you to vitrify first frozen water and then macromolecular objects, and he did this with many samples. And in fact, actually, the way that Jacques Dubochet vitrified his specimens in the 1980s is exactly the same way that we still do today in the EM suite at Scripps. We have the exact same manual plungers that they used back then. Of course, a number of the tools have been roboticized since then, but many people in the facility still prefer to use the old manual plungers, including myself. So the vitrification technology was developed in the 80s. There were a number of developments. So the first demonstration that you can use EM or cryo-EM to image protein molecules at near atomic resolution was really demonstrated by Richard Henderson in 1976 with a reconstruction of purple membrane protein, bacterial rhodopsin, using electron crystallography. So not single particle analysis, but electron crystallography. And then about 15 years later, he then derived an atomic resolution or a near atomic resolution structure of bacterial rhodopsin using improved methods. And the single particle aspect, so based on the slide that I just introduced, the single particle cryo-EM and the methodology surrounding single particle cryo-EM, alignment, classification, ab initio reconstruction, and so forth, refinement, these have really been developed in the 1980s, throughout the 80s, 90s, and continuing into today. The methods are continuously improving. And there are a number of very good methodologists in the field who are continuing to push the ideas. And of course, for these developments, specifically for these three developments, but I think these three people will be the first to say that it was a community effort. That of course they were pioneers, but it was really a community effort in the field. But these three, Jacques Dubochet, Joachim Frank, and Richard Henderson earned the Nobel Prize in 2017 for their work in developing cryo-EM for high-resolution structure determination of biomolecules in solution. So Jacques Dubochet for early vitrification technology, Joachim Frank for a lot of the computational methods, and Richard Henderson for a lot of the the first high-resolution structures and a lot of the theory and really vision underlying EM. This is just the latest of, I think I counted something like 25 Nobel Prizes that are in one way or another related to structural biology. So in recent years, what has happened? I think a lot of people started to take notice around 2013, 2014. And the reason for this, or one of the primary reasons for this, is the introduction of direct electron detectors. Okay, I think many people in the field will tell you that actually it has been a steady development, even throughout these years. But the introduction of these direct electron detectors has improved resolution to such a point where all of a sudden other people in the field started to take notice. Okay, and this dramatically, this of course increased the visibility of the techniques and the applicability to actually understand really macromolecular structural biology. So what are these detectors? So the old CCD, charged coupled device cameras, basically have, so you have these pixelated detectors, you have a scintillator for converting, and then you have the detectors are, so you have pixels for capturing electrons, you have a scintillator for converting electrons into photons, and then you have a detector for reading out the photons. Okay, so so if an electron comes in, hold on a second. Okay, sorry. Let me go back. All right, so these are the old CCD cameras. Okay, so in the absence of any sort of noise, okay, so if and this is your so this would be your image. Okay, so in the absence of any sort of noise, the electron would come in, okay, and it would form a perfect image in that particular pixel of the detector. Okay. In reality, what happens is that, as you saw, the electron comes in and it scatters. There's backscattering events, And what happens is that the image that is formed is not sharp, but it's actually spread out across a number of pixels. Okay, so that's in the CCD, these CCD detectors. Okay, the direct electron detectors don't have a scintillator. So in fact, what they have is a back-thin set of pixels that would directly detect electrons, rather than converting electrons into photons that are then read out by the camera. Okay, and so by directly detecting these electrons, this allows you to remove a number of the backscattering events and improve the readout at the level on your detector. Okay, so this improves your what's called detective quantum efficiency. Okay, and also decreases the point spread function. Okay, so these detectors have a better what's called it's a DQE, essentially, which effectively describes the signal-to-noise ratio at different spatial frequencies that are read out on the imaging medium. The other thing that has improved and has been introduced in these new detectors is the ability to record movies rather than still images. Now, the reason this is important is because as soon as your electrons hit the sample actually starts to move a little bit. Okay, and so that is seen here. So, okay, so if this is your sample, your electrons will hit the sample, and the sample actually starts to move. Okay, and there's various charge-related effects that contribute to sample movement upon exposure to electron radiation. Electrons are negatively charged, which leaves a partial positive charge on the sample, and so these charging effects will then lead to various unpredicted or we don't yet know how to predict them. Movements of the particles and, in fact, the entire ice sheet as the sample is dosed. Okay. So, so now the new detectors, okay, will allow you to record movies. Okay, and so then you have frames as the sample is moving. Then you have frames of the entire of the recorded movie, okay? And so then if you have these individual frames, then of course you can align them, okay? And by aligning the frames, you can then account for the beam-induced movement. Okay, so this would be these older CCDs which have poor detective quantum efficiency and are also corrupted by the image movement. These are the newer direct electron detectors, which allow you to record much crisper, much nicer images. And this was just experimental data from Nico Grigoriev showing the real effects with rotavirus particles. And you can really see that these particles are moving in this direction. Whereas if you account for the movement, then you can recover this information that is lost during the readout. And this is just a slide showing the improvement in the DQE. The improvement is essentially in the signal-to-noise ratio at different spatial frequencies between direct detectors and conventional charge-coupled CCD detectors. So this led to what became known as the resolution revolution. Now, I would argue that perhaps it wasn't a revolution per se. There was a number of very many developments from different corners in different areas of the field, all of which culminated in increased, people paying more attention. And once people started paying more attention, then of course they realized that actually this technique could really be used to understand interesting questions in structural biology. And this also led to a rapid increase in the number of users and cryo-EM users and practitioners. And this is just the plot showing the cumulative depositions of cryo-EM structures into the EMDB. And so with sort of some of these inflection points around 2013, 2014, now really is going up and up. As I said in the beginning, there's a fairly large depth of field in EM, which allows you to image molecules with and specimens with different size ranges. In the case of single particles, these are some of the different size ranges that have been imaged to, I believe, I think all of these have been imaged to near atomic resolution. Now, dengue virus, I don't know, does anybody, so here's a scale bar, so 200 angstroms, maybe about 800 angstroms or something like this. Right, so 80 nanometers, right? So that's for, so actually that, so for single particle, that's quite large, but of course, EM allows you to image much thicker specimens than just 80 nanometers. Okay, but for single particle analysis, there's, I think one of the points that I would want to make is that for single particles specifically, there really is no upper size limit for in practical purposes. So if you can isolate your macromolecular object of interest, you can, and in sufficient quantity and purity, homogeneity, then you can certainly image it. Now, there is still a lower size limit, although that is getting pushed basically on a yearly, if not monthly basis. So this was a couple of years ago, 2016, and at that point, there was a Subramanian's group. It described this IDH molecule was a little under 100 kilodaltons. It was the smallest molecule that was solved at that point to near atomic resolution, which was quite challenging. So with Will Kantara in the audience and Cheng Zheng, we described a method where you can, so in order to image smaller molecules, so the reason why smaller molecules are challenging is because they they're difficult to see, right? So they're difficult to see. The signal to noise ratio is much smaller, so they're difficult to see, difficult to align, and to deal with using computational methods because of the amount of noise relative to signal. And so, but if you can scaffold them to particles such as ribosomes or other large symmetric molecules, then you can better see these particles, and then you can zoom in on these scaffolded either proteins or RNAs. In this case, we used RNAs, and be able to better derive structural information. Now, some of the problems with this particular approach is that, depending on how you scaffold, you have, flexibility of the molecule, which will add additional challenges to the analysis. But so we show that you could do, quite a bit better with scaffolding and focus classification compared to without scaffolding, or compared to without focus classification. And an RNA molecule like this, you still would not be able to derive in the absence of scaffolding. It's too small. But with scaffolding and focus classification, you can at least get some information. Of course, this will be limited by how much flexibility you have in the molecule. And more recently, actually, this paper came out, or it's a manuscript, it's a preprint, came out on bioRxiv. This is from Gabe Lander's group. They showed that using conventional cryo-EM and using a 200 kilovolt microscope, you can actually image proteins that are quite small. This is a kinase, pKa, I believe. This is a pKa molecule. It's packed into these, packed into the holes. So these are all single particles, and they can obtain some two-dimensional class averages and derive a preliminary three-dimensional reconstruction at about 6 to 8 or something like that angstrom resolution of this 40 or 50 kilodalton pKa molecule. Now they're still not yet at atomic or near atomic resolution. But this is just to say that the methods are continuously improving. And my guess is that with better detectors and better ways of treating the data, one should be able to get pretty close to near atomic resolution relatively soon. The differences, so there are analogies between X-ray and crystallographic and cryo-EM workflows. So with X-ray, you have a purified sample. Arguably, has to be really pure because you need to grow crystals. The data you are only collecting amplitude information. You're not collecting a phase information, and so then it is an iterative process of phasing and deriving the atomic model. Okay, there are analogies with EM, albeit with a few key exceptions. So you also need a purified sample. Arguably, it doesn't have to be as pure. So instead of growing crystals, we vitrify the sample into liquid ethane. And rather than collecting diffraction data, we are collecting real space images. So the scattered diffracted electrons are then refocused into a real space image. And really importantly, with X-ray, we are collecting an ensemble. These are ensemble images, right? But with EM, these are individual particles. Okay, and so it's fundamentally a single molecule technique, which actually allows you to understand structural heterogeneity in interesting ways. And so because we're collecting real space images, we don't have to rederive the phases. This allows you to then directly build a reconstruction and then directly derive an atomic model from that reconstruction. Now there are still a number of bottlenecks with EM, and so with X-ray, arguably the major bottleneck is in growing crystals. Okay, if you can grow crystals that can collect good diffraction data, then deriving the atomic model, depending on the quality of your phases, depending on your initial model, whether you have an initial model or not, this may or may not be challenging. Okay, but of course, in many cases, it can be a major bottleneck. And arguably, the sample has to be really pure because you don't have the ability to computationally purify the sample through using methods to analyze structural heterogeneity. Now with EM, this part is relatively more simple, but we still have bottlenecks in data collection, image processing, and reconstruction. And so the latter part of the pipeline is much slower. In fact, orders of magnitude slower. So the advantages of cryo-EM are that it requires less sample. So compared to X-ray, about an order of magnitude less sample. Purification is not as stringent. There's no crystallization, no space problem. And really importantly, we have the ability to understand structural heterogeneity because it's a single molecule technique. Okay, so both compositional and conformational heterogeneity. The disadvantages is that there's still lots of workflow details to iron out. We're arguably getting there, but we're really quite close. But you know, maybe can't quite yet reach atomic resolution. Although I think you know it's pretty close.
The standards are less established. The data collection is much lower, and there's still a lower size limit. But as I already mentioned, this is also getting pushed on a routine basis. So we are actively working towards atomic resolution. And I guess it depends on what you call atomic resolution, whether or not you can, atomic means whether you can resolve carbon-carbon bonds, 1.5 angstroms or not, or whether you want to see carbon-hydrogen bonds or whatnot. So this is to some extent a matter of semantics, but we are working on true atomic resolution. Something that we did over the last year is so we noticed that so we were working with a particular specimen for it was AAV for technical reasons, and we noticed that we knew that there weren't any really real reconstructions that have been solved to less than 2 angstrom resolution at the time. So this was late 2017. And we knew that there was no, so the resolution was in practice limited to about 2 to 2.5 angstroms for the reconstructions that have been deposited into the electron microscopy databank. And what we did is these were two, so this was a student and a postdoc, Youngzi Tian and Shriram Iyer. Youngzi has been a fantastic collaborator over the last couple of years, and Shriram Iyer, he's a postdoc in my group, and they basically worked out methods to improve the single particle workflow to derive a high resolution reconstruction of AAV. Okay, and in this particular case, we resolved the structure to about 1.8 to 1.9 angstrom resolution. This was enough to completely define essentially all of the amino acids for the stable parts of the virus. So every single one of these atoms or atomic groups with hydrogens has a bump associated with it. Now you can't quite distinguish, one bump from the next, at least if you think about this, like the Rayleigh criterion, right? But they all have bumps. Okay, all of the aromatic residues, they have holes. You can clearly distinguish tyrosines from phenylalanines, for example. So we're really now starting to see all the details, at least with select specimens, so well-behaved specimens. And this is just so if
you look at one particle to the next, you see the different rotamers.
Yeah, you could see different. You could definitely see different rotamers. Yeah, absolutely. In fact, you can see multiple rotamers depending on. Yeah.
We are averaging together all of these.
Right.
Not one particle makes it special.
Right.
So you have to average ones that are similar.
Right. So they are averaged out. So it's about 30,000 times 60 in this case. So it's 2,000 asymmetric units that are averaged together. So you do right. So let me clarify a little bit. I mentioned that it's a single molecule method. Okay, but you still have to average in order to some extent to improve the signal to noise ratio. So in this particular case, we had to average 2 million asymmetric units in order to improve the signal to noise ratio to this for 2 angstrom resolution. For ribosomes, which I think Dario and Jessica are going to be working with in the tutorial, we get 3,000. We get 3 angstroms with 2 to 3,000, something like this.
Yeah, I just remember seeing James' talk where he used basket.
What's that?
Okay.
Battery's dying. Oh, okay. My battery's crap. So I just have a few slides left, and then I'll.
How large does the structural difference have to be for you to be able to classify them out? Because you can imagine you could have like a large domain movement, which might be easily separatable versus something like a rotameric state. Would you notice that if you tried to do like a larger group of classification and then you have like a fuzzier area, you might try and separate those out into different like phenylalanine rotamers or something.
Yeah, it's a very good point, and we're not at the point where we can classify out individual rotameric states, at least not. But it's a very good point. Yeah, it might. Yeah, maybe. Well, yeah, maybe. Yeah, I hope so. Yeah. And we are actually, one of the most exciting aspects about this map is that we're actually seeing the initial traces of hydrogen atoms at a resolution that was relatively low compared to what we think of with X-ray. So these little bumps right here, these are actually bumps contributing to bumps from hydrogen atoms at about 1.8 angstroms resolution, whereas with X-ray diffraction, you typically see them at about 1.2, 1.3, maybe 1 sub-angstrom. And the reason for this is because the image formation is different. So the X-rays you have, so that you're generating electron density, but here with electrons, we're not actually looking at electron density, we're looking at the potential, electrostatic potential. And so the mechanisms of image formation are actually slightly different. And so the effects, what we're actually seeing is slightly different. This is just showing some of the advances, the resolution advances in cryo-EM by year, and we were quite happy that our map was basically the actually for a period of for a number of months we had the world record for resolution in single particle or in cryo-EM, which I was quite happy with. We'll take it for what it for the amount of time that it lasts. But of course, since then there was a few other structures that came out that were now higher resolution. So we described to 1.8, and then a few structures have come out of apoperatin that were at about 1.6. So the continuous advances. And maybe so that I won't. Yeah. They're all. Yeah, right. You have to symmetrize, and you have to. Yeah.
In fact, the part is the difference between looking at the code and like acids inside.
That's right. Yeah. That's right. I mean, so sorry. What was his name? He was here, and he was here a few weeks ago. He gave a beautiful talk from Oxford. Juha Wiskanen from Oxford was here a few weeks ago. He gave a beautiful talk about how you can use computational methods in single particle analysis to focus in and essentially deconvolute or focus in and deconvolute the density of the nucleic acid of the DNA inside of a virus of a viral capsid. And sort of look at trace the entire path of the nucleic acid. So I think in the interest of time, I'm going to stop around here. I'm just going to stop. I'm just going to mention that there are still a number of efforts a number of things that remain to be done in order to reach true atomic resolution and to get to higher resolution, higher throughput with single particle EM. One of these, so of course one of the main problems is that we need to reduce some of this remaining beam-induced movement. Okay, this still remains a problem, and I think that what we're limited by now between 2 angstroms and 1 angstrom is actually this residual beam-induced movement. Of course, better detectors they're already coming on the market, and they're going to improve things. Aberration-corrected microscopes are going to make things better. Better computational tools to extract resolution from the data. Even the data that we already have right now. As we keep the data for many years to come, because the tools get better and you extract more information from the data. Of course, we'll have more automation, smarter microscope utilization, and larger data sets. And then one of the key challenges that unfortunately I don't think I have time to talk about, but actually it's better methods and better tools for specimen preparation. Okay, specimen preparation remains one of the principal challenges in the field, and I'm not just talking about the biochemistry. Okay, I'm actually talking about specimen preparation for imaging. Let me see. Can I do 5 more minutes to talk about? Yeah. All right.
In the higher
yeah.
energy artifact, I guess, right? Does he have more sample movement there? Particle movement?
You know, I'm not sure. I'm not sure if it's more or less. So with 200 kV, I guess so these are, well, they're lower energy electrons. So I would expect it to be, perhaps be more, but I'm not sure they've done these quantifications. Well, I know they haven't done side-by-side comparisons with the pairs. Yeah. Yeah. I'm so with sorry, for what?
When you mentioned Gabe's paper.
Oh, why are they able to use 200 kV to look at smaller particles?
No, and I was just wondering, is the issue with resolution more significant than that?
Oh, I don't know. Yeah, we don't know. Yeah, I mean, I would expect it to be more significant at 200 kV, but I don't think they've done these comparisons. So, okay, I will talk about this just to introduce the problem that specimen preparation remains a very major problem in cryo-EM, and there's ways to deal with it. But so this is how we make our specimens. Okay, we basically apply a sample onto this grid that we hold in tweezers. Okay, and then we blot out excess sample and then plunge freeze it into liquid ethane. Okay, so 99% of that sample, 99.9% of that sample is discarded. Okay, you're using a big giant piece of macromolecular filter paper. It's got like all, you know, I mean, if you ever look at a filter paper under a microscope, it's not a smooth thing, right? You know, so you're using this big giant piece of filter paper, and you're expected to get really thin ice that is, you know, 20, 30 nanometers in thickness. Okay, so this is not a good way of actually making specimens, but it works. Okay, but one of the problems is that specimens actually adhere to one of two air-water interfaces. Okay, and so if under ideal conditions, okay, if you look at a cross section of a grid and you think of how specimens would adhere, or sorry, how specimens would behave in the cryo-EM grid, you would think that they would adopt random orientation inside this vitreous layer of ice. Okay, and so that, you know, if you have an even layer or kind of a little bit concave or convex, you would expect them to adopt random orientations inside this layer. Okay, in fact, this is completely not true. Okay, what the specimens do is they adhere to one of two air-water interfaces. Okay, and this is just experimental data from Alex Noble and Bridget Carragher. Okay, showing they did acquired tomographic data of about 50 different specimens, okay, and basically showed that every single one of those specimens, perhaps with the exception of this glycoprotein sample, adheres either to the top or to the bottom of the air-water interface. Okay, over 95% of samples do this. Okay, this is just a slice of the tomogram showing that the specimens are either at the top or at the bottom of the air-water interface, and basically what this causes, okay, is if you take something like hemagglutinin, okay, this is the top view of hemagglutinin, and this is a side view, what you end up seeing is just, in the case of hemagglutinin, you just see this one view, okay? You just see these top views. And when you perform a reconstruction, if you're just looking at these top views, then you perform a reconstruction, the actual map becomes smeared along the Z direction, okay? So your resolution is good in XY, but it's really crap in the Z direction. Now, what we've done is we actually showed that you can take these specimens, okay, and so here they are adhered to one of two air-water interfaces, and you can tilt the sample, and by tilting the sample, you can actually acquire more of the because of the geometry of the imaging conditions, or because of the geometry of imaging in an EM, when you tilt the sample, and then you can acquire more of the different views, and this allows you this allows you to better fill up reciprocal space for these preferentially oriented samples. So it's just based off of simple geometry, but what this does is that you can take a map that looks like this, which is pathologically anisotropic, and really you can't get any meaningful reconstruction out of it, but you can actually get quite a nice reconstruction. And we showed this last year. Since then, and we showed that you can derive a reconstruction of hemagglutinin to about 4.6, 4.4 angstrom resolution. And since then, we deposited this data set. This data set was then picked up by a number of people developing image processing methods. Again, keep the data. and actually, this particular data set has been pushed to about 3 angstrom resolution, a real 3 angstrom resolution. Okay, and I expect that as methods improve, that others will improve on this even more. Yeah. It's a general solution unless your protein aggregates and dissociates at the air-water interface. Otherwise, it's a general solution. Yeah. And
would that be affected by changing the pH or the soil processing?
It very much could, yeah. But I think that will then be might be specimen specific. Yeah. And so we've had now a lot of success with this method, and I'm keeping track of people who are using it, and actually there's more and more papers coming up now using it as a solution to the air-water interface problem. And I think I'm just going to stop there. I'm going to acknowledge. So this is the group, and I think now Dario Passos and Jessica Brunn will give you the cryo-EM tutorial. The people who did some of the work that I described, Young Zitan was really spearheading a lot of the high resolution and the tilting methodologies, and then later with Sriram Iyer, Phil Baldwin. He's a mathematician in the group who is now trying to derive really theoretical framework for understanding anisotropy and how it affects resolution. And of course, the TSRI facility, Bill Anderson, he's been just amazing at really maintaining everything and having the microscopes functional. So, and thanks for your attention.
Comment on about sample preparation, about blotting.
Mm-hmm.
So, is it preferential to them or?
It's a good question. So we blot. Traditionally, we always blot from the front. Okay. There may be some advantages to blotting from behind, and the reason I'm not sure whether or not this has been rigorously investigated.
Start. So my name is Daryl. I work with Dimitri Salk and Jessica. That's the second part of the tutorial. We were going to start the hands-on part. We tested these computers last week, but we didn't wait for so long just to see if the VPN would hold. So yes, that's a practice issue. So initially, what we envisioned was that we would have each computer, we have 15 computers, so each computer starting here from 1 to the last one, there are 15, we would have different accounts, because the program we're going to practice today, called System, you can load multiple programs with the same account or the same database. So then we split all the database. We have 15 files.
Oh, hang on. Oh.
I think you guys have access to.
Doesn't matter which computer it is. This is a guidance to help you install. There are numbers on. Yeah, we're sharing. Yeah, that was.
I'm gonna get 3.
There must be a form to the matrix.
And the other thing that we can, the other thing that we can. This is that. That's 8. This is 9.
So here we have their artistic structure of the 6S ribosome that Dimitri and I published in 2015 at 2.9 angstrom resolution. And this is the data set we're going to use today for the tutorial. The difference is that for this data set, we use almost 2,000 micrographs. And for today, for our tutorial, we just chose randomly 100 micrographs. So we don't expect to go to 2.9 angstroms. So basically here we have a slide for showing you guys from the electron microscopy data bank the different programs, the amount of different programs that we have available to process cryo-EM. Here's a list anyone can access. I don't expect you to see the details here. So this is why I amplified here the programs. We are gonna just go quickly through them and see the pros and cons for each of them. And in general, those are the programs we daily use in our lab. Here we have a long list of different programs that they are going to do different things. But here are the programs we use to process daily in the lab. They are the most used programs in our group. So Epion. So Epion is this application platform. It's very interesting design. It was released. This program was released in 2009 by Gabe Lander. Yes.
Could you get out of this mode and just? I think it's. Yeah.
Is the slide showing? Because it was recorded that way.
Yeah. Yeah. I don't want to. I don't want to show it. Okay.
Here?
The orange arrow.
Oh, here, right? Okay. Thank you. So here we have the Epion. What is great about, so this program was developed and released in 2009 by Gabe Lander. Dimitri is also part of the development. They developed at Scripps. And what is very interesting and useful from this program is that it communicates with Legionome. So Legionome is the software we use to collect data on the microscope. And what it does is it will save all the information we use it for the data collection. And that in practice, that is going to give us two advantages. First, we don't need to re-enter all these values. And second, it reduces the chance for us to make mistakes, which is very common in the field. So here we have like the magnification, the pixel size. So the dose is always recorded. And then once we start the program, it's all saved. So we don't need to keep entering all this information and increasing the chance to make mistakes. So this is great for this program. And second, it's a platform, not just a single program. And that's ideal because once you want to do, let's say, the city estimation, you have access to multiple different programs. And in our field, this is very valuable because in practice, we are always trying multiple programs to see which one will provide us better results. Since the data sets in general are very variable, in practice, it's hard to find a recipe to process in just a single way that will be better than any other way. So in general, what we constantly do in the lab is we are often using multiple programs to extract the best information out of it. What is not good about Epion is that it's very complicated for maintaining. and keeping it updated. So that's one downside from the program. Other than that, I really like it. Yes.
Does this integrate with EPU as well?
It's just Legionel. So they are like you can use either of them. If you use EPU, you're not gonna have all this information saved on EPU.
Okay.
So what is also interesting, as you see here, you have all the micrographs. So you can see all the micrographs here, the unaligned, which misses the A, and the aligned micrographs. And then you can delete it, or as you see here, you can delete trash, or you can hide the micrographs you want. So it's great. It's in general, when you're collecting data, you have very bad micrographs, and that's a way that I like a lot to exclude the bad ones. So the other program we often use in the lab is the FreeAlign. It was developed by Nico Grigoriev, that is from Janilia farm in Virgin. He developed this program in 2007. And what is good about it is because it's very flexible and dynamic. So if you want to do 3D classification and refinement, this is ideal because you can definitely play with almost any parameter, and that's going to give you better results, especially for complicated cases. And it's incredibly efficient for 3D classification and refinement. What is not good about it is that it's a command line program, so that makes things more complicated it makes things more error prone. But if you are advanced, that's not a problem. And also it's not practical for beginners, and it only does 3D classification and refinement. You won't do 3D classification, you won't do particle picking, all the other steps we know it's important. So the other program is one of the most famous programs we have on the market right now. All these programs I'm presenting so far, they're all free. You don't need to pay for them if you are in a non-profit institution or academic. So here you have Relion. It was developed by Shores in 2012. And that was one of the GUI programs that was very user-friendly. And this is one reason why it became so successful. And plus, it started to use a GPU, so that accelerated a lot the processing. Although right now we have some pros and cons to use GPUs, but at that point we were thinking that yes, GPU could accelerate a lot the processing. In practice, we see now that some programs, even running CPU, they can also be quite fast and can generate great maps. So it's a safe way for you to start from scratch to the end and get a good map. Just follow the tutorial that is available for the program from the program, and the chance for you to make mistakes are just reduced. So if you have a simple data set, you should be able to go from the beginning to the end.
Back in to check GoToMeeting, open up this arrow. Okay, so is it recording now again?
Negative point about this program is that it's limited in options. So what I mean about it is that if you're using FreeAlign, as I said, you have multiple parameters to play, And if you are using Reliant, you have limited parameters to use and change to improve your reconstruction. I had just one extra point, but that should be considered because now they are implementing command line as well for Reliant last version, the updated version. So the other program we have is cryo-electron. Was released last year, 2017. Became very famous to be a light program, very user friendly, and also efficient, very efficient. So here is the way cryo-electron works in practice. So we were submitting, like here, say here I imported micrographs. So you have the micrographs. I perform CTF estimation. You have CTF estimation. You have here 2D classification. Generate an ab initio map, and then you can start to pick your particles. Sorry, yeah, this is one step. I pick the particles here. I generate an ab initio, and so it's a very light and efficient program. So what I like about it, it's user friendly, very user friendly. It runs on GPUs, so it's fast. It's really fast. It's been the fastest program I've seen last year. It's so it's fast and practical. Its 2D classification, it's very good. So it's, to me, in problematic data sets, sometimes is the one that performs better from cryo-electron. And it's for sure, in my opinion, the best ab initio 3D reconstruction program available. And the new version offers several new tools. So we should be able to do many other things that we used to not last year. So what is not good about it is that outputs have limited compatibility with the other programs. So it still have cryo-electron has some bugs they are trying to fix while they are developing and implementing new tools. So it's not everything will work. And one of the things that bothers me a lot is that if you move your data set to cryo-electron, it will be hard for you to move it back to whatever program you're using. So then here we have a system. This is a program we are gonna use it today to process the data. So what is great about the system, so the system was developed by Timur Grant, Alexis and Nico Grigoriev, the same person who developed FreeAlign. This is a CPU program. It's fast, it's friendly, and provides you great 3D refinement or 3D classifications. What is not good about is that the data is saved in SQL database, so that makes things more complicated for you to extract information from your data. You can get a reconstruction, and later on will be a little challenge for you to find out what particles have contributed to your final map, which is not the case when you use Reliant. Reliant, everything is very visual. You have these text files that are for easy access, so you can manipulate almost everything in your processing. Here is everything is in this database, so it's a little more complicated to access. And also the GUI, this window here that hopefully everyone has open in your computer, it needs to be open in your physical computer in order to have the program running. So in this case, we are using this XGO, so we are virtually running the GUI. But if you kill the GUI, the program will die. That's not reality for the other programs. So system, you can close the window. Reliant, you can close the program, and the program will still keep going. System, if you close this window, the program stops. So this is something that hopefully will be updated soon because the program is very good. Okay, so here is the data set. As I said, we are gonna use it today as a template for the hands-on tutorial part. That was published by Dimitri and I in 2015. As I said, 2.9 angstrom is a 60S ribosome structure. And just to Dimitri, I'm glad Dimitri did a great presentation that it will help us to follow all the workflow for processing. Here I'm just gonna revisit quickly the workflow. So we have then data collection, we do frame alignment. After you have your frames, as I just showed in Epion, you can hide bad images, you exclude them. You can also mask out the bad regions. All these things, they are each day less useful because the data are getting so good that you are not in need to remove ice or pieces of ice from your microbatch any longer. So then we perform the CTF estimation that Dimitri explained. We are going to correct the final image to account for the errors the microscopy will add. We do the particle picking, then we're going to create the stack. The idea to create the stack is we're just going to combine all this information to further move it to the 2D classification, or we can also move straight to 3D reconstruction using a supervised or unsupervised classification. Then we can do we can go for the map refinement and build a model. That's the workflow for cryo-EM processing. So first step, we start the processing by aligning the frames. This step, it won't be done here because we did it before. It takes a while. So we did it for you. Basically, what we see here, Dimitri has already talked about. We have just a square from the grid. Here we have the holes. Here you have your image. And here is before alignment. Here is after alignment. You can see the difference as Dimitri also showed before. So in system, what is very good about system, what I like a lot, is that you can import any step of your data set through just tabs here. So you can import your moves, you can import image particle positions, you can import 3D volumes, and even refining package. So if you were using other programs, you can go straight to refining package and just refine it here using system. You don't need to do everything here. So this is great. And so here is from where we're going to start. We're going to start from the image. So I imported them. So in all computers, we should have these micrographs available. They are already aligned. So
let's just make sure that.
Does everyone see it? For those who are already can visualize this screen, we can move to the first step that we are in practice really going to perform here, which is the CTF estimation. So to do the CTF estimation, we can go to action, go to find the CTF. Then we are going to open this page. Just go here, open the expert options. And this is what we should see. This data set is really straightforward because the ribosomes are beautiful, are large, there is a lot of signal. So in general, all these parameters here, we could easily use the default. But if you have a more complicated data set, you're going to have to play around with these parameters to improve the result. So for us, we can use the 512, 384. I don't know what is set in your computer, but you can follow what is suggested if it's 384 or 512. If you were already here, then you can just start processing. Yep. So then basically, if you were able or not to run this is what you would expect from the CTF estimation results. So you're going to have a list of all micrographs you performed the CTF estimation. Here, I just did it multiple times with different parameters to see. And then you have here this I selection here is the micrograph you are checking. So you can inspect each micrograph to see how it looks like. And here you have this plot that will basically tell you how well is your CTF estimation fitting to the power spectrum of your image. So that is going to give you a resolution that is cut. Yes.
Point, you use the mouse or point with your finger.
Okay. This is too light.
Like an LCD screen.
Okay. Let me move this down here. Yes. So.
The mouse is better. Yeah. You do the mouse.
Okay. So I'm going to use the mouse here. So all this blue curve here will be the quality of your curve or the quality of your fitting, and that's going to provide you this resolution that we have here on the right side of your this slide. So if we change it here to the next image, we are going to see again how this CTF estimation has performed, and then you're going to have estimation for resolution of your micrograph. So basically, what is important to consider from here, whatever you see as your CTF estimation doesn't necessarily mean it's going to be your final it would be the final resolution for reconstruction. That is an estimation for the quality of your data set. So if you see that it's estimating 100 angstrom, something probably is wrong. So the next step, we should just go here to actions again, just tab on the left side. Then we would go to find particles and show display expert options, and that's what you're going to see. What is also great about system is that we have this sort of menu on the right side that anyone is a very simple language. It sometimes doesn't explain detailed things, but it's very useful for you to change or choose values for the parameters like here for your processing. So I add a red circle to the most important things that you should be able to play and see differences in your result. So the size of the particle is important to play around to find a better value. This threshold height is also important. You can check this square here to avoid high variance areas. So this is usually going to remove particles from the ice or the carbon if you have it. Sometimes you do this and you're also going to miss some particle peaks, real particle peaks. Then this is why you need to play around. Here you can check and you're going to see the display of your image instead of the manual. So you're going to be able to see your image here on the right side. And then you can, on time, follow what each parameter you are changing is doing. And here is also, I wish we could do it here and see the difference, because I played around and I've seen it very nicely. If you check this, you can see you can play with the distance from the edge of your micrograph. You're gonna exclude for particle picking. So then, once we find a good condition of the ideal parameters for our particle picking, remember, so this is an important thing for who is starting. You're never gonna have your perfect picking. You always are gonna have to choose between how many good particles you pick and how much noise you're also gonna pick. If you completely remove noise, you're also gonna miss particles. If you decide to pick all particles, you're gonna also pick noise. That is a trade-off. So here is what you're supposed to see for the results from the particle picking. In this case, ribosome is pretty straightforward, so we can see that it's picking quite well. As I said, we have still some particles here that we can't see as picked, but another tool that I think is very interesting for this software is that once you are at this stage, as I said, you can go one by one micrograph per time, and you can manually select the ones that they were not selected automatically. So if I come here to this ribosome and I press it here, it will also select this particle. This is great. So once we are done with particle picking, we go to the next step, because if you try to do 2D classification from here, you are not able. So this red message here is saying you can't perform. So what you need to do next is you need to, as you wrote here in the bottom, you need to create a refinement package. This is how the software works. Yes, sure.
So what's your criterion for when you decide how many particles? As many as you can, except the ones that are on the edges, or is there any qualitative assessment that tells you I took a lot of garbage or I could take more?
This is so challenging. So this is so challenging that nowadays we are tilting most of our data for the reason Dimitri explained it earlier. Most of the data, most of the particles will have some sort of preferred orientation. So we are tilting. Once you tilt your data, sometimes 40 degrees, if you have very poor signal for your particle because it's a small particle, you barely gonna see your particle during the peaking. So when you consider that you are tilting, it's even harder to find a condition where you're gonna pick particles in a 40 degrees tilt and in the non-tilted.
The way the software decides it's a particle by a certain that can fit in a certain box of expected size, and then
right.
Noise ratio or somehow something like that.
Yep. Each program will perform different. They have different algorithms behind them. The one that I like a lot, I didn't show here, is it's a sort of a new program. It's work. It has been very efficient for tilting picking, but in general, all these programs, they will pick well, unless you have problematic data.
If you touch the particle like you're doing, does it give you that should be added to your data set, or does it give any kind of early criteria whether it's useful information you can, contain? No. How do you, going back to what you, there's jump and there's good, and you start collecting.
Right. So yeah, that's a good point. So let me clarify one thing. So in general, especially nowadays, before we used to be very concerned to bad particles we were picking. Right now, in general, you don't need to care about it.
Oh.
If you have ribosomes, even if I pick carbon surface or selecting regions in the carbon, I will be able, during the processing steps, I will be able to remove and exclude those bad particles. Yes, but nonetheless, it's also important to know that if you have very poor signal, as I was saying, if you have 40 degrees tilting and your particles are 100 kilodaltons, the noise will look just like your particle. And that is when it starts to become more problematic, because now you need to be more concerned to what you are picking. Because if you pick too much noise, now the noise will also average. Yep. And then you're going to have a class average that are just noisy. So it's a balance between what you have and what you really can do. Did I answer more or less? Okay, so then the next step is, as I said, we're going to do the 2D classification. Basically, we can go to assets, create. Then we are going to follow this wizard here that it's pretty straightforward. There is no other option because we just started the project, so you won't make any bad decision. You just go all the way. You're going to create refining package, which is this one. So what we have in this refining package, we're only going to have the CT estimation we just obtained, as well as the particle picking coordinates. So all we have here is this. So we have all the micrographs here, and we have it X and Y position, the position for each particle we picked. We have the pixel size, so all the information we also obtained by CT estimation, which is here the focus 1 and 2. Once we have now this stack, now we should be able to go for the 2D classification. So the 2D classification, what we do, so nowadays is the same. We go back to the same question for the picking. Nowadays, we don't necessarily need to do 2D classification anymore. So the data sets are so good that if you just make a stack and you go straight to the 3D reconstruction, in some cases, you're going to be able to get a decent reconstruction without even to remove things from the 2D classification. So, but before, that was essential to do. And what is the idea to do 2D classification? It's pretty much just to remove bad particles. That's the major idea to do 2D classification. You just want to average the particles, average all the particles, and be able to remove, to exclude things that don't resemble your particle.
Do you think that
generates different conformations?
You're gonna have a class average that will provide you different orientations.
During the
yes, 2D classification will show you how these particles they are displayed in your image.
Orientation.
Well, you don't get
Yes, orientation.
You don't have orientation.
You don't have
Whatever-
values for the orientation.
whatever is in-
Yep.
Whatever is homogeneous in the 2D image.
So we
Yep.
do either conformations or orientations.
Right.
So then again, for the ribosome, for this data set we selected, we chose, you should be able to just go for the default values, and this is what we can get. So if we go back here, just go to actions, to declassification. This stack we just created will show up here automatically, and then you can just start classification here, and it should run. It would take you around I think 10 minutes to complete.
How many, hey, Dario,
Yes.
How many cores do you have people running on? 10? It looks like 10, yeah, this GE 10. Okay, that should be okay.
Yeah, yep.
If it's more than that, it'll go.
It's 43. I think it's 43. It's 43.
43.
Yeah, I used the default. I didn't add the.
Do you have options here?
They don't have options. I didn't install.
Oh, okay.
Yeah.
43, okay. Actually, the cluster should be okay.
No, I don't think it would be an issue because we have very few computers that are actually working.
No, now everybody's working.
And this thing is very
We got everybody on SSH, now everybody should be working, I think.
good. And this is so, yeah, that's. So
I'm getting stuff, but not.
is every
It's identified when they appear in this panel.
As it
These are all particles from many different. So that's four days. Now, I lost my eye right on some of these. A couple issues.
Yeah, eventually they'll start looking like that.
Actually, I don't know how many. The first is just. So
this is the 2D classification. We selected, some of you didn't have a chance to see in details that we selected 10 class average. So we have here 10 class average. What we are doing is we have this different multiple or several different particles, and the 2D classification, as we said, we're just classifying these particles to remove bad particles. And what it does is pretty much it does rotation and translation. So if we have this like particles that they look like this, and when we took the image, they are in different orientations. So it will just rotate and average out. So then one question that Ryan asked me that is a good question for you to consider. So how many class averages we choose when we are going to process? So that is also relative. It sounds just like the particle picking. It depends pretty much on how much bad particles you have in your data set, how many bad particles you're also picking. Because if you pick too many bad particles, you know that, because during the particle picking here, you realize that it's picking things that you know are not your particle. Then I would choose a larger class average. And the reason is, if you choose just 5 class average, and you have 100,000 particles, you're gonna have to fit these 100,000 particles into the 5 class average. So if you have bad particles, they will just classify as good into one of these 5 class average. So the chance for you to exclude bad particles is it's very unlikely that you're going to be able to remove bad particles without to remove good particles as well. So then in practice, what I usually do is I first analyze how many good particles I have per bad particles. If I have 10% of bad particles and I have 100,000 particles, I will probably can just choose like 100 class average, and probably one of these class average will contain most of the things that are garbage. And if you see the results are not ideal, you can always go back and reclassify with the larger class average or number of class average or lower.
So is it always better to have more class averages?
It is, but it has the computational weight. And second, you still need to consider one point. If you have just 100, let's say 100 particles, and you choose 100 class average, you're going to have just one particle per class average, so you won't have enough signal. So,
I mean, fundamentally, you're bidding the data, right? You're grouping the data into it, right? And so a rough rule of thumb that some people have followed, although it may not necessarily apply to some of these later programs, but 100 particles per class is a rough rule of thumb. With some of these later programs, they tend to
reduce. Yeah.
They tend to pool particles into class averages that have higher resolution, and so maybe you could do 1,000 particles per class. Okay, just keep in mind that you're bidding the data. Okay, so if you have an orientation like this, and you have 1,000 particles in there, so that one particle will be like that, another will be like this, another third will be like this, right? And you're averaging all of that. So you're losing information, a little bit of information, right?
So how do you set the bidding boundaries for something like this?
You mean, so again, how
So
many you
there's a
choose, or?
structure, there's one with like this, there's one with this, but there's some similarities between the structures, and those are each bid into separate particles.
I guess,
this is
how do you define that it's a good cross correlation or not?
This is a clustering problem, right? This is your traditional clustering classification problem in computer science, and you have to define a metric where your signal is at a specific resolution is above noise, and then in principle you can choose an optimal number of classes, right? But in practice, we just try different ends.
So you don't set like you have to be, some kind of arbitrary cutoff to bid them and then I can look at it again? Because
when you say arbitrary cutoff, you mean by the number of classes, of course, right? So the arbitrary cutoff we usually do is 100 classes.
Okay, got it.
Yeah, that's simple, and it usually works. Okay.
But depending on the number of unique sort of orientations, is there an inherent disadvantage to having sort of redundant classes?
Yeah, exactly. It ends up getting bigger. So yes, there is. Jamie Williamson talked about this, at some point in one of the HIVE meetings. One of the projects that we have with him is understanding ribosome heterogeneity, in that particular specimen, the ribosome is constantly assembling between a sort of a half-assembled form and a fully mature form. Now there we're doing 3D classification. We're not doing 2D classification. We're doing 3D classification. But we can see essentially the continuum of structural heterogeneity between a half-assembled subunit and a fully mature subunit. And then, and what we're then trying to do is we're trying to probe deeper and deeper and deeper to figure out how many true classes can we actually interpret, given some biological given a biological framework for what we want to interpret as real density, right? So then we essentially define heuristic criteria as to how much density we want to interpret, and then we have a pipeline for then defining the number of classes.
It reminds me one very important point to consider. That is a tip. When you are removing class average, be very careful to what you are excluding. Sometimes you might not see a great signal from one class average, but you might be getting rid of an important orientation or particles that will contribute to orientation that you're going to miss in the end. So it's common that if you delete some class average, you want to get a 3D reconstruction, descent to 3D reconstruction later. So sometimes it's better to just keep what you are in doubt than exclude. This is why most of the time nowadays, in my case, for example, I'm not even doing 2D classification. I'm skipping this step. So here is just the difference. We just talked already about it. If you have 10 class average, if you have a 5 class average, so so then we were moving to the ab initio 3D reconstruction. So we have 2 different ways to generate the reconstruction. When we have a reference or when we don't have any reference. In this case, we are going to start from scratch. We are not going to use any reference. So we need to reconstruct the map based in the, so we need to assign the angles for these particles without any reference. So this is what we call ab initio 3D reconstruction. And if we are all online, you can just go here to the actions, ab initio 3D. And again, for this data set, the default values, they should be enough. You don't need to change anything. And then you just pay attention to the number of starts and the number of cycles if you are going to do for your real data set at some point. For here, you can just start refinement on the bottom here.
Right, so we're ready for the break?
Yeah.
All the refinement always goes down to the raw particle. And for each raw particle, you refine or you assign your optimal orientation angles, which means translations X and Y, and then your free Fourier angles, like 5 beta psi. So in the refinement that Dario is going to show right now, you're optimizing your orientation parameters for the raw particles. You never go back to the class average. Class averages are not used. Right? Class averages are primarily used to visualize in 2D what's the homogeneous, what is homogeneous in the data, and primarily we use them only to essentially clean out that clean data.
Right. Yep. There were other programs like Epion used to consider 2D class average for the ab initio, but this is no longer a reality.
We used to use class averages quite a bit more because they have higher symptom ratio. But now the program has evolved, and now we don't necessarily.
What happened to your limited space of the
Yeah.
I thought that you were using class average for example as well.
3D class averages. So 3D classification, not 2D. You can see things in 2D, okay, but it's an important caveat. You know, one of the slides I talked about the projection, and the projection, I didn't find much of the projection can correspond to differences in orientation or different structural states, and you don't know. You may not notice.
So quickly, this is the auto refinement. So you're going to have a plot showing you the particle distribution. Usually, if you have preferred orientation, you're going to see that your data is distributed in very specific. Sorry, I'm sorry. Yeah, I forgot. You're going to see that your data is represented in very particular regions of this plot. Here you have this FSC curve showing the resolution that you can see here. And for auto refinement, just taking advantage from what Dimitri said about the 3D classification, you can also use the auto refinement to classify your particles. So if we had here we just have in this tutorial, we have 3,000 particles, so we can't classify this. This is too little data set. If you have 100,000 particles, you can create, there is an option here in assets. When you go to assets and create a package, you can create a package to split your data in 3. So then if you split your data in 3 during the refinement, what you're going to do is you're going to classify 3 different distinct classes. And that is the time where you're going to be able to visualize structural differences in 3D space. So we also have as a tool here besides the right side of auto refining, you also have the manual refinement tool, and that is you have more parameters to change, to play, and you can only run manual refinement once you run auto refining. So this is how the program works. But then here you can tune. It's a very similar program to FreeAlign. So here you can tune more, include the CTF re-estimation of your data. So usually this step helps to improve the quality of your maps. Here is a result from the 3D manual refinement. Looks just similar to auto refinement. You have the plot for angle distribution, particle angle distribution. Also have Fourier, and you also have here the slice. So then in system, there is also this tool here that is generate 3D. You can use it to generate half maps. Half maps are necessary if you want to use it further for FSC analysis and other things. So then here you can use this tool to generate half maps.
So one of the metrics that we follow every day of map is good is FSC curve. And to make a gold standard FSC curve, you split your particles that went into this 3D refinement into two groups of refining, and you refine them independently and then compare them. And you compare against each spatial frequency, so basically at each resolution shot, you're comparing them, and you see where the correlation is in all the customers. That's the drop off, and that's how we determine the resolution. That's what the half maps are used for.
Right. This is the gold standard resolution that we use that is currently accepted to measure a resolution in cryo-EM. And here is the result from this Generate 3D. We also have another tool, is the last one here on the right, to the top your right side, which is the sharpen. So the sharpen will sharpen your map that should filter and improve let's say the signal of your map, information you have in your map. Here is the result, how it looks like once you plot. You should see this sharpened curve dropping. And here is the final slide for this part of the tutorial, just showing on the left side before sharpening, and the right side in let's say beige, the after sharpening. So you just have more information in your map. Jessica will talk in more details about Chimera tool to manipulate or to play around with your maps and structures and models. Yep. Questions while Jessica is coming to start her computer?
Okay, my mic is on. Okay, so I'm Jessica Bruin from Dimitri's lab, and I'm going to do a Chimera tutorial. Okay. So there should be this document on the desktop for you to follow along with. And there's also a link to Chimera on the desktop. So Chimera is a really great 3D visualization tool for cryo-EM volumes in ways that Pymol is not particularly good. And so I know a lot of you probably maybe came from crystallography like me and aren't as familiar with Chimera, but it's a really valuable tool that's worth the time investing to learn how to use this well. So we're going to start with just kind of a basic, part one is just fitting an atomic model into an EM density. So if everybody can launch Chimera, the first step is to go to File, and we're going to do the Fetch by ID, which is a nice feature. And in here, you can select what database you want Chimera to search from, and it'll just pull out that, it'll download and load that density for you. So in this case, we are going to load 8140. So this was already downloaded on my laptop. It'll probably take you a little bit of time to download it. So this is a mononucleosome that was solved by Cryo-EM to 3.9 angstroms. And so you can look at it here, and if you right click, you can rotate it around. If you left click, you can zoom in and out and kind of get a sense of things. Sorry, thank you. thank you. Yeah. Yeah. Left click is twirl, and then right click is zoom in and out. So one of the first things you'll notice when you open a volume is that this little volume viewer box pops up. You don't want to close that. You want to leave that open. And this plot here is a histogram of different thresholds that you can display your volume at. And so you can take your volume and slide this little bar around, and you'll see that at these lower values we get a lot more noise, and this isn't very easy to look at. And then way up here we're only seeing like the most intense intensities there. So and one other thing is we're also going to change the step size from 2 to 1. So this is basically a binning step where now we've unbinned completely and we're at step size 1. And so you'll see, and here you can see alphas with little sidechain bumps, which is great. This will make the program run slower. So sometimes running it at the lower step size is easier on your computer, depending on how fast your computer is. So one of the things I wanted to point out was that people who deposit densities into the EMDB, they will tell you what threshold you probably want to display their structure at. So on the EMDB website, you can click on the details link here, and this will pop up a second page with experiments and validation. And you'll note that the authors are telling you that you probably want to contour this to 0.27. These values are going to be different for different structures, so it's sometimes nice to look and see what the depositors prefer. So we'll go ahead and you can type in that value over here. So what I set it at 0.23 is pretty close to what they're saying is optimal for viewing. So it changed a little bit, made it a little clearer. So. All right, so the next step is we're going to make this density transparent by clicking on this little gray cube for color. And this pulls up the color editor box. And in here, you can change the color if you want by sliding these bars around. You can also type in a color that you want, like blue or whatever. That is a very aggressive blue. So let me stay there. So from that, but the last bar in here is actually the transparency. So you can slide this around to a transparency that you like. Since we're going to be docking in an atomic model, it might be nice to have it a little bit transparent so that you can see how well it's fitting in there.
If you don't see letter A, check box opacity.
Sorry. Thank you. Yeah, this box. Yeah, apologies if I've obviously tricked out my Chimera. There's a lot of I have all these nice little shortcuts on there that I have added in because I like them, and you can do the same by finding a tool that you like, Rainbow, and adding that to your favorites. Anyways, there's a lot of nice ways that you can make your life easier in Chimera, but I'm not going to go into them today. Okay, so we've got our volume transparent. So now we're going to open up an atomic model. So we're going to open up PDB 3LZ0. And this is not one that was actually built with this EM map. These depositors didn't build a map, but they stated that this X-ray structure was closest to their EM model. So we'll see what we think of that. So again, we'll do the fetch by ID and type in 3LZ0 and fetch. So I'll take a little bit for it to load. And so you'll probably want to zoom out to be able to see that. So again, that's right click and hold to zoom out. And then you can see both of the models have loaded, but they're nowhere near each other in space. So there is a tool in here for fitting that model into your density, but you need to first get a first approximation that's pretty close. It's not smart enough to go from this and just fit it right in. So you're going to have to line them up manually to start. So to do that, you're going to go to Model Panel. So in Tools, General Controls, Model Panel. So Model Panel is a really important thing that doesn't automatically pop up, but it's good to kind of know where it is. So right now we have all of the models that are loaded right now listed. So there's the map and there's the crystal structure. And you can check and uncheck the show boxes, and that'll make it disappear and disappear. One of the things to note is that right now both of these models are active. So even if I hide that nucleosome and then I like move things around and rotate, if I click back on the EM map, it's still there and it moved relative to the other one at the same time. So that's important to keep in mind. So the thing we're going to do now is what we want to do is hold one constant and move the other towards it. So we're going to move the crystal structure to the EM map. So how you do this is you make the only one active the crystal structure. So I unchecked the A for the EM map. And now when I go in here and I rotate things around, only the crystal structure is moving. So the first thing is to kind of line it up roughly so they look like they might, if I move them, they might line up. So I did that with like left click and hold to line them up a little bit. And then with these, the magic mice, what you need to do to move it is press Option and then left click and hold, and that you can drag the molecule with that. So on a 3-button mouse like mine that has the scroll wheel, you press down on the scroll wheel and it's much nicer. But yeah, so I'll move that over and get it kind of lined up. And once I've got it a little bit lined up there, I'll activate both. And I'll rotate 90 degrees and I'll see, oh, I am still a bit off in that dimension. And then I'll go back. I'll again deactivate the EM map and then scoot the crystal structure over. And then activate both again and kind of see how I'm doing. And this, you might want to take a couple of tries to get it pretty close. It doesn't have to be perfect, but it does need to be kind of close. How is everybody doing with that part? And does anyone want some help with moving the crystal structure around? Huh? Is the mouse dead? Oh, so it's Option and left click to move. And I guess I mistyped. It's that's left click to rotate. And then I may have mixed that up, and I can't test it over here because I don't have a magic mouse. But it's
yeah, left click rotates, Option left click translates.
Okay. Yeah, thank you.
Are they centered?
Yeah, so there's that's a great question. There's several ways to do that. You can in your model panel. I think you can type it in here. You can type it into command line. Oh yeah, to load the command line, you would do tools, and then I believe it's yeah, general controls command line. That'll pop up a command line for you, and you can type center. Another way is that if you select oh yeah, so if you select one of the maps, I believe you can center in here. You can center the volume as well. Once you're in the ballpark, you're going to go to the volume viewer, and you'll go to Tools, Fit and Map. Okay, so volume viewer, Tools, Fit and Map, and a little pop-up will show up, and you'll tell it I'm fitting the crystal structure into the EM map, and you'll hit Fit, and that'll pop the last little jiggle that needs to happen to get it perfectly in there. You can kind of rotate it around, look, and make sure that it did an okay job. Also note that it gives how many atoms are outside the contour, which is nice to keep track of. And you can get a sense of what percentage of the PDB file wasn't in your contour. So yeah.
So like, what's a good rule of thumb for atoms outside the contour being bad? Like 10%, 5%?
Probably 10%. I mean, it depends on how reasonable your map is. So a lot of, like Jess's 50S ribosome structures, a lot of those proteins are just missing, and so you've got all these atoms outside, but the rest of it fit well. So yeah, number of outside, it's like you should maybe just delete those atoms,
so
and then
it seems like this is more of a subjective viewing thing rather than an objective number to look at per se.
It's quantitative, and I think if I was refining this model myself, I could then use this as a metric to judge how well my refined model fits. Yeah. So another fun thing with the nucleosome in particular, because you have this DNA and it has this each like full turn of the helix, what we can do for fun is if you rotate this about one full like 10.5 base pairs around and then try and refit, it usually will, oh no, I popped it back, right. Let's see. So here, yeah. So here I've forced an incorrect fit. You can see where I've just rotated the nucleosome around relative to the density, and you can see that it was really trying to match up that the DNA and the double helix there, and so the DNA is fitting pretty decently, but then the protein's not fitting well because it's misaligned here, and there's this big alpha helix that's not in the correct spot. But again, this is another, if you're not close enough with that initial attempt at fitting, you can be thrown off by thinking that this model doesn't fit at all. This is a terrible map for it. But again, yeah, that was just me rotating it a little bit, and I can rotate it back and hopefully fix it. All right, was everybody able to fit a structure into, does anybody need any help with that step? So I'll say we have this optional, if you want, you're welcome to load this other PDB that I recommended, step 11, and try and fit it in and see how well it fits. I'm gonna just skip that and continue onward to part 2. So in part 2, we're just gonna play around with some of the visualization options, give you a flavor of the sorts of things that you can do in Chimera that might help you better understand your structure. So one thing that can be nice, this is a really nice map that has been post-processed and sharpened and masked and everything, and so there's not a lot of speckly dust everywhere, but sometimes maps that maybe, initial maps that come from the Lundquist lab maybe have a lot of speckly dust everywhere because we haven't really polish it to the point where we're ready to deposit. And so for those maps, you might see stuff like this creeping up, and there's little speckles everywhere. So that can be hard to see. So one of the ways that you can get rid of that or hide that dust is a tool called hide dust. So you go into volume data, and there's this hide dust option, and a little window pops up, and you can basically just try the default and click hide. So that got rid of a lot of this little dust. You can also move the sliding bar around to see, like how far is too far, that sort of stuff. So that's kind of nice, a nice tool to be aware of. This hasn't deleted that data. That data is still there, and if you save this volume as an MRC, it's still there. Part 2. So we're going to try a tool called Rainbow. So you'll go to View, or Tools, Depiction, and Rainbow. This is just a very quick way to make looking at an atomic structure easier. So you can do it by residue, which gives you the nice, kind of like chain bows in PyMol, where the N termini is blue and the C termini is red. In this case, we have lots of chains, so I would actually recommend I have a shortcut for me, but anyways, you can do chain instead and apply. And so this is colored every single chain a different color, which maybe makes it easier for you to understand what's going on there. And you're like, oh yeah, I can see there, my 8 proteins in the octamer and 2 strands of DNA winding around. So, all right. So next, you might be interested in finding a particular residue in this structure. So we're going to go to Tools and Sequence, and then Sequence. So this will pop up yet another window, and you can display any of the chains that are available in all of the models that are open at the moment. So that'd be a ton of windows. So we're just going to work on chain A, which is H3. And so this has popped up a little window here with the residue sequence. And one really nice thing about Chimera is that it will, if there's information in the PDB header indicating all of the residues that were in the crystallization construct, it'll include those even if they're not modeled. So everything in this red box, that's the H3 tail that's not resolved in the crystal structure, but it's nice to see that sequence. So in here, this is the first visible residue in the structure, this is proline, and it goes all the way to this arginine. And Chimera also does these yellow and green denotations. Does anybody want to tell me what they are? What these parts of the sequence correspond to? Yeah, so it's secondary structure. Let me just clear that section. Yes. So the yellow is for alpha helices, and the green is for beta sheets. So that's just a nice little helper for you to navigate around. So in our case, I ask that you highlight the first visible residue, this proline 38. You can see down here, it's telling you the number. And if you just click and kind of drag across it, you can highlight that one residue. And so now we've done something where we've selected in some portion of our models. And with that, you can go to actions and do a lot of things to just that one particular thing you've selected. So one thing that might be nice is I'm like, oh, hey, well, where is it? It's going to be highlighted green, but there's a lot of stuff going on. It's hard to tell where it is. So if you go to action and focus, it'll take you right into that residue. So it's right here. So that's nice. And all right. So what I was suggesting you do is do actions, atoms, bonds, and show. So we'll show those atoms and bonds. So the default show is the sticks. and but maybe you don't like sticks and maybe you want spheres because they're a little bit bigger and easier to see. And then maybe you want to color it something, so do magenta just to make it easy to see. So yeah, so we've just labeled the N-terminal residue of chain A, which is maybe nice to do. So if you did end up doing that, this focus, and now you'll notice that I'm viewing this in kind of a weird way, and the structure is pretty sliced through, and this is maybe a little bit annoying to view or maybe easy to view. So this is, you can change this by going to Tools, Viewing Controls, and Camera. Oh, sorry, Side View, that's what I meant. But it's all in the same menu. And this pops up a look at how we're viewing the structure. So this is our camera with this little yellow box being our viewpoint, and then the physical slice that we're looking at down here. So you can click and drag these yellow lines to include the whole structure, and that might be easier for you to view. Is there a question? Or? No. Okay. All right. So that. All right. So we've highlighted this N-terminal residue. I've also asked that you go in and label that C-terminal residue, but I think I'm going to, again, skip that for time constraints. So one other thing with these selections is, so anything you select gets highlighted in this green color. And until you tell it otherwise, it's going to still be selected. So right now I'm done labeling and dealing with that residue, and so you want to deselect it. So to do that, you go to Select and just Clear Selection. And so now that's done, and I can't perform any more actions or accidentally think I'm selecting something else. So, all right. Yeah, and then just for fun, I had us take an image on its side, in kind of this, where we see the whole structure in the background, where you can do that by going File and Save Image. And in here, one of the things that I really like is doing this transparent background, because that just makes it nice and easy to pop into PowerPoint or whatever. So you can save that. And then you can also, so this camera side view can be really nice for getting better images. You know, maybe now it's hard to see that N-terminal residue, but if we clip in, maybe it's a little bit easier to understand what's going on, and this might be a nicer way to make a figure for your papers. This isn't quite as necessary for the nucleosome. It's a pretty small structure, but when you're dealing with the 50S or the 60S ribosome that Dario was showing you, it's a really big volume, and maybe clipping in will help you see better. And yeah, that's our next thing, is to open those. So, all right. So once you're done having fun playing with this nucleosome, we will shut down Chimera, just completely close it, and we'll reopen a new session to open up the maps that were generated from system. So, so the first thing is I'm going to have you manually copy over those. So these are volumes that Dario has already prepared by following his system tutorial. So to copy over those files, you're going to open up a terminal. So it was that little black icon on your desktop, somewhere this guy. And then in here, you would type in SCP, this stuff.
This is only for application finished.
These are actually finished. So these are ones that Dario made that we're going to open up first. If you happen to have something that finishes, this is the way you would navigate to it and copy it over. So this is why I made you guys manually copy it over. So, so yeah, if you copy that text from my Word document and hit enter, a thing should pop up and it might ask you a yes/no authentication thing. Oh, I'm not connected to the VPN, so I can't do this.
Yeah, this is
Yeah, copy and paste. Don't try and type it because you probably make a typo in the maps that that Daria made for us. So yeah, so one thing to note is when you have multiple volumes loaded at the same time, it can be nice to, there's this little eyeball kind of icon that's your visualize or display on display. So you can turn that off to just look at one. And again, they're both active, so they'll both rotate around for you. Definitely close them, yeah, no, it's okay. So a couple of things are reduce that step size to 1 and slide around your threshold value. So do that for both of these. I also recommended in here, I mean, I encourage you to play around with sliding that bar, but I've also written in some nicer values to type in to view. So for the volume _81, for that guy, I was using yeah, 7.5 and then 6. So this does have a bit of dust showing, but you're also able to start to see some interpretable density in the unsharpened versus sharpened. So, and you'll note right away that it's much easier in the sharpened map to start to make out the double helix of the double-stranded RNA in here. It's a little bit easier to deal with.
Yeah. Yeah, you got it.
All right. So here I've hidden the dust and just set them to a nicer threshold to view, and they're both active right now. Maybe I might have went too far with the dust on this one. The gray is, yeah, I went too far on my hiding of dust. So that is the one scary part of hide dust, is it's just looking for little bits of density that aren't connected to other density. And so if your map is a little bit discontinuous like this guy is, it might over prune in an inappropriate way. So something like that might be more appropriate. All right. So bonus points to anybody who really knows their large ribosomal subunit and can tell me what's wrong, or knows RNA and nucleic acids just really well. Like somebody who can point out, what's wrong with this structure that chimeras, that system just spit out automatically for us. Like we can zoom in on this is a helix here, and so if you're really well versed with this, yeah, exactly, exactly. So we got the hand wrong. So this is an inverted map, and so from in the data processing pipeline, it's difficult to distinguish between the handedness of the structure that's going to output, and so 50% of the time your ab initio model that it spits out is going to be in the wrong hand, and
we lose information, you don't have hand information.
Exactly. Yeah, it's impossible to tell until you get here and you know things about the way that RNA goes, like which direction the helix should go. So if you ever get a map that's the wrong hand, which again, if you're doing ab initio, it's about 50% of the time you're getting it the wrong hand. The way that you deal with this is we're going to do something called a Z flip, and Chimera can do this. So you're going to go into Tools, General Control, and then this command line. So is everybody seeing this little command line section at the bottom of their Chimera GUI? Everybody got that? I went to Tools, General Controls, and then Command Line, and now it should pop up at the bottom. So this is a really nice thing to have. And in here, we're going to do a little command, which is VOP, zflip, and then you'll do one of the models. So, so you also notice that each open model has a designated number. So right now we have a 0 and a 1 open, and you can see that this volume is number 0 and this one is number 1. So whenever you're doing command line stuff, it's good to keep track of which model is which number. So right now I'm going to zflip the unsharpened map, which is 0 with the order I opened. So VOP zflip that. And what that did was it created a second map for me. So I can see, and it also, you'll want to change the step size and change the level probably. So, oh man, did I crash Chimera? Yeah, if you zoom out, you can kind of compare these two maps and see for yourself that it has flipped it. Hopefully. I think I did crash Chimera. But go ahead and zflip the sharpened map. And, oh, okay. Yeah, so this is one of the things where when you're loading such large files, sometimes it is nicer to keep that step size smaller so that it's easier to deal with, because it's computationally taxing on your laptop. So we'll zflip both. You'll also notice that in the volume viewer, there is this little minus sign, which you can use to just close maps that you no longer care about. And for me, I'm absolutely sure that the hand was wrong with those initial maps, so we're going to close the two that were the wrong hands and just not deal with them anymore. And that hopefully will make my Chimera run smoother, is to just close them. So this little minus sign will close that permanently. So those are closed. So now I just have my two maps.
After you do the zflip, can you save that and use that for refinement?
Yes, yeah, and re-upload it. Chimera, or sorry, System is also smart, and in that sharpening option, there was a little box to check that says zflip for me. So sometimes you can just not actually sharpen, but just zflip. And CryoSpark has that as well. And I rely on, I'm not sure if it has it in there, but yeah, you can always upload back in the correct hand. And I usually try and identify this right away and flip it to the right hand. But when you're working at such low resolution, sometimes it's a little more ambiguous if you don't know what you're expecting. So, all right. So we've got our zflip. Yeah. It's just when you go to fit atomic coordinates in there that you have a problem. So, all right. So now we are going to go and load up the very beautiful, final, polished, sharpened, masked, like heavily processed deposition that Dimitri and Dario, yes, ready for publication. So this was like an initial, just quick half a day, like what is a small, like this was not the entirety of the data set that we gave you in System. It was only 100 micrographs. I don't remember what Dario used, but it was a very small subset. So we'll show you what a nicer, the entire thing, and then also lots of nice post-processing and using the absolute most optimal data processing pipeline that they could do at the time. So yeah, So we'll load that up. And again, you'll want to drop that step size to 1. And you might want to, again, go to the EMDB to figure out what threshold you should be using, or just use your own best judgment. But yeah, so that blue one looks really nice, far nicer than either of these two maps. So for, yeah, so this is the deposited map where you can, you know, this is much easier to look at. You can really see, so in here we've got the RNA double helix, and so these are phosphates and some nucleotide base pairs there. You should be able to make out some alpha helices. Yeah, right here's like a nice alpha helice with little bumps of side chains and stuff. So, so one thing that you can do right now is you might want to align all of these models together. So just a reminder, well, you would go to Tools, General Controls, Model Panel to get this back, where you can, I would fit 1 by 1 to the EM map. So for that, you would make it so that only one model is active, and then kind of flip it around until it fits in there. The other thing I want to point out for fitting in or aligning things is that once you do hit that command line and you have this bottom part, you can easily check which volumes are active down here, and you don't have to go to that extra model panel window. So this is another tip and trick. So rotate it. And then again, to do the final fit and map step, you would do volume viewer tools, fit and map, and pick, right now I'm doing, sorry, the unsharpen into the EM map, click fit. It's taking quite a bit longer because again, it's a much bigger structure. That's why I had us open the nucleosome. It's tiny and easier to work with. So. Okay, that one looks good. Awesome. All right. So whether or not you've actually fit them, that's fine. I did want to show one last small thing, which is this tile option, which can be nice when you're looking at multiple volumes at the same time. It can be nice to separate them out, and especially if you're looking at 25 volumes at the same time, you can hit that and then you can kind of compare them at this bigger kind of global view. So to do that, in the command line, just type tile and hit enter. If you're sick of being in the tiled and you want to be back into normal, you could just type reset. I'll go right back. Oh, okay. I didn't. Yeah, so that reset back to the non-aligned coordinates, and I needed to actually have saved those volumes in that moved configuration to get them back. But anyways, All right. And then, yeah, so you can open up the PDB file that was deposited with this structure if you want. I think if anybody has any system tutorial, any ab initio structures that they've created right now, it might be kind of fun to try and copy those over and open them. We do end in 7 minutes. So if anyone's really ambitious and wants to try copying over any of their intermediary ab initio files right now, that would be, that might be kind of fun. But yeah. Yeah, the ones you've been creating. So you would have to navigate to them. Yeah, so in your HIM folder, which would be like data 1 / HIVE 2019, there'll be then a file named Max, I think, and then your personal Mac number, and then in there, if you can navigate in those folders and find files. I think I don't have quite enough time to but if you're savvy with terminal, maybe you can find them. So. Yeah. Yeah, so if you were on, actually, I can actually load up. Does anybody have a pretty far along ab initio we're on that they might want to look at, or is everybody pretty? Okay.
We tried.
You tried?
I wasn't very far.
Was it just a sphere or something? What Mac number are you, Jared? If you look on your.
I'm at like 20 something iteration. First, I kind of crashed my computer, so I can't really do anything.
I'll see if you have anything worth opening.
Yeah, so we can actually customize this.
Yeah. Yeah.
Should we get a running, a few people running refinement from like a good and a bad ab initio?
Yeah. Yeah.
And that should finish it up, I think, right?
Yes. I'm not sure how they can. Let me see what they look like when the job is not actually done.
But I still don't understand. I don't think you should be able to run a refinement even if you don't have an ab initio finished. I don't understand why you can't do it at the same time. They're two different processes.
I would think so, but
They just crash,
yeah,
crash the database?
I'm not a, yeah.
Sounds like one of those bad commercials.
Two structures, the gray and yellow came from computer 4. This cyan and purple ones came from computer 8, and then the other two are from computer 9. And these are, so this first one, or the number 1, 3, and 5 are all the ab initio structures that popped out. So these are clearly much lower resolution, but in some of these, you can start to see features. So let me just hide. So certainly in this one, you can, if you look at it by this angle, it does sort of look like that crown view of a 50S or a 60S ribosome, if you're more familiar. I'm pretty sure this one needs to be Z-flipped. And this one as well looks, this is looking pretty nice as that classical view that everybody shows for the 50S ribosome. So, and here you can start to see some RNA double helices showing up, so that's nice. And then this one was not as nice, and it's hard for me to tell. Yeah, I mean, I know that everybody stopped their ab initio runs before they were even finished and just took whatever they had so that they could launch it. So this one was not as great. And and you can see, so for this one that was not as good of a initial ab initio model, the reconstruction that you get in the end is really poor and doesn't have much continuous density, very, very speckly. So this is from this one. So this one was probably the best ab initio model to go in and refined. It looks like this, and you can you're still retaining some of those nice structural features. This one's looking a bit more believable. And then looking at this one, so this was like a lower resolution, but still probably correct ab initio model. And the refined model is pretty speckly, but still looks like a 50S. And I just wanted to show you some of the metric outputs. So yeah, so this is from computer 4. And we'll see that this was the output from system from the refinement. And you'll notice that it's telling you that this is a pretty high resolution structure, that it popped out 3.8 angstroms, and you're like, yay, I won. But when you look at this FSC curve here, it doesn't look as nice as we would like. It should be a bit flatter, and then fall. This is falling off a bit too shallow, I suppose.
What does this mean when they launch like that?
It's probably gets kind of lumped into this term just called overfitting, which is just, yeah, we're over parameterizing things, and this is not a particularly good refinement based on the shape of this curve. So what I would argue was the winner from this is from computer 8, which I like the shape of this FSC curve a bit more, and from the actual structure. So this is reporting an actual resolution of 5.6 angstroms, which is maybe closer to reality, just looking at those densities that were coming out. And so even though, yeah, I guess this is like one of the big takeaway points is don't always like look at that resolution number it spits out. You know, always want to open your maps and make sure you're getting something reasonable. So yeah, that was about it. I don't know if there were,
Which one did that correspond?
This one, sorry, this one was from, I didn't open all three, but this one was from this one. So yeah, the starting ab initio, where you clearly saw a lot of secondary structure features, and then this was the final map. So where here I can make out some helices and stuff. So yeah, yeah, it's pretty nice. You can see like the this portion here is where the peptide synthesis happens, and yeah. So anyways, that was really fun. Thanks everybody, and thank you for letting me steal some time.